Greetings ladies and gentlemen, my name is Ryan Shazani and welcome to another video. In today's video we'll be doing some physics, and more specifically we'll be trying to derive the moment of inertia of a sphere. I won't be going to the specifics of what exactly the point of moment of inertia is, but I'll start off with the mathematical expression for moment of inertia. It is defined to be I equals to the integral of r squared dm. What do I mean by this? So if I were to have just a mass, I'll take any point, right? Any point of mass. So you take, and then you draw a line intersecting the midpoint of the object, and you take this mass times this radius, and you'll take times this radius squared, and you'll do that for every single point in this object until it covers the whole object, and then you add up for everything. You add up everything, you'll get moment of inertia. Okay? So, the question that we'll be tackling today is the moment of inertia of a sphere. So, let's start by drawing a sphere first. Now, we'll be given the information of the mass of a sphere, which is capital M. We'll be also given the density of the sphere, which is rho, and we'll also be given the radius of the sphere, which is capital R. So these are the given information. Now, to tackle this question, we have to be able to imagine a sphere being made up of an infinite number of disks. What do I mean by this? If I were to cut up this sphere, I can actually represent it like this. You can imagine the sphere being made up of an infinite number of disks if I were to just cut it into layers and layers and layers. But it doesn't stop there. One disk can be also visualized to be made up of an infinite number of rings. So this is the key concept that we have to understand to be able to integrate the I, or r squared dm, because you have to do integration twice. So the strategy that we'll be taking today will be to find the moment of inertia of one disk. So how are you going to do that? We'll be trying to find moment of inertia of one ring and expand it from 0 radius to radius equals to the full disk. And then we'll find the expression of I disk, or moment of inertia of one disk. Then we'll integrate it from the bottom disk to the top disk. So that is the technique or the strategy we are going to be using today. So let's start doing some actual math. So let's start by drawing the diagram more clearly first. So this will be the variables that we're dealing with. This is the midpoint of the sphere. Let's draw the disk. So this is the midpoint of the disk. So this is capital R, the radius of the sphere. And the radius of the disk can be represented by r sine theta. And I'm going to be making another variable here, which is theta, because I want to make this r sine theta, right? So what is theta? Theta is the angle between the vertical line intersecting the midpoint of the circle and the point where the edge of the disk touches the edge of the sphere. And I'll be making another variable, x, which is the vertical component, and the infinitesimal of it will be dx. Alright, so now let's imagine the disk itself. The disk itself is made up of infinite number of rings, but I'm just going to draw one ring, and this is the midpoint. So if I were to draw this, you can imagine that this is actually just r sine theta, right? Now the radius of this ring, it will be represented by small letter r, and therefore the infinitesimal thickness of the circumference of the ring will be dr. Okay? So what we'll be trying to find is I disk equals to r squared dm, but this is just the expression. We don't really know what this means. So dm, if you have to think about it carefully, if I were to just find I disk, dm actually refers to the mass of just one ring. So I can write this down to be dm equals to m ring. M ring is actually equals to m disk times the area of a ring over the area of a disk. Okay? This is just based on the law of proportionality. Now, let's continue. M disk, area of a ring. So, if you were to imagine, area of a ring is this right here. So, it's just the circumference, which is 2 pi r, times the thickness, which is dr, over so 2 pi r dr over the surface area of this whole disk, which is pi r squared sine squared theta, and can simplify this to be m disk 2 r dr over r squared sine squared theta. But the thing is, we also have another unknown, which is m disk. How are we going to find m disk? Same law, same technique. M disk is equals to mass of the sphere times the volume of the disk over volume of the sphere. And this is just capital M. Volume of the disk is equals to pi r squared sine squared theta times the thickness, which is dx, over volume of the sphere, which is 4/3 pi r cubed. Okay, so substitute this. Before that, we can just simplify this to be 3 over 4 sine m sine squared theta dx over r. Okay, now I'll actually just get 3 over 2 m sine squared theta, but it will cancel out, so we'll need that, and then r dr dx over r cubed. Okay, so now we are ready to find the I disk. So substitute dm to be into here, so r squared 3 over 2 m r dr dx over r cubed. Now, the question is, what are we going to integrate? We're trying to find the moment of inertia of one disk. So what we're actually trying to do is, from the ring at radius equals 0 to the ring at radius equals to r sine theta. So it's actually just with respect to dr. So 0 to r sine theta. And to express this more clearly, you can just write 3 over 2 m dx over r cubed. Integrate from 0 to r sine theta, r of 3 dr. Okay, so this is the integral that we'll be working with, which is a very simple integral. It's just 3 over 2 m dx over r cubed, r for 4 over 4, 0 r sine theta, and this is just 3 over 2 m dx over r cubed, r for 4 sine for 4 theta over 4, and this can be simplified to be 3 over 8 m r sine for 4 theta dx. Am I right? Over 2 r m. Yes. Okay, so this is the simplified version. So I'm going to erase all of this now, and we'll start to find the moment of inertia of a sphere. And how are we going to do that? So write down first, I sphere is equals to the integral of this whole thing, 3 over 8 m r sine of 4 theta dx. But the thing is, if you were to be working with dx, right, it'll be from x equals to negative r to x equals to r. So from bottom to top. But it's a bit complicated and it's very messy because you have a theta and a dx. It doesn't match up. So what can we do now is we can convert this whole expression to be just in terms of one variable. And we'll try to change it into theta. So simply, we know that cosine theta is equals to x over r. So x is equals to r cosine theta. So dx, differentiate this to be negative r sine theta d theta. Then we can just substitute this. So I'll get r, I'll get integral over 8 m r sine of 5 theta and d theta r squared and negative. And now because we're working with d theta, we can actually, instead of making it from this angle to this angle, we can just times 2. So minus 2 from 0 to pi over 2. So this is the expression that we're working with. And you realize this is just negative 3 over 4 m r squared 0 pi over 2 sine power 5 d theta. So essentially we're just trying to integrate sine power 5, which is a very simple integral. Let's try to do that. So sine power 5 can be broken down into sine power 4 times sine, and then this will be equals to sine squared theta squared sine theta d theta, and we'll make a variable which is u. So write down let u equals to cosine theta. So du is equals to negative sine theta d theta. So I'll get this to be 1 minus cosine squared theta squared sine theta d theta. Then I'll get this to be 1 minus u squared and I can actually just substitute this, right? So this will be minus du, and simplify this to be negative 1 minus 2u squared plus u to the power of 4 respect to du. Okay, then I can just simplify this to be so this will be just u minus 2u cubed over 3 plus u to the power 5 over 5. Yep. Okay, so we got this. Now we can just substitute this to be in here. So I'll get 3 over 4 m r squared pi over 2 0. Substitute this. U is equals to cosine theta, so it's just cosine theta minus 2 cosine theta cubed over 3 plus cosine of 5 over 5 respect to d theta. Okay, so simple, am I right? Let me check. Yeah, because the negative cancels out. Okay, so we have that already. And from here, it's just a matter of just substituting the numbers. So I'll get this to be, remember, Yep. Okay, so I'll get this to be minus 3 over 4 mr squared, and then sorry, this, because I actually integrated it already, so it's from 0 to pi over 2. Okay, so okay, cosine 0 is equals to 1 and cosine pi over 2 equals to 0. So it's just 3 over 4 mr squared. So minus 1 plus 2 over 3 minus 1 over 5. Yep. And from here, this is just 3 over 4 mr squared 8 over 15. And if I were to simplify this, divide by 3, so this is 5, 4, this will be 2, so it'll be 2 over 5 mr squared. And voila, I of sphere is equals to 2 over 5 mr squared. A very simple derivation of the moment of inertia of a sphere. If this helped you out, like the video, subscribe, and thank you for watching, and I'll see you in the next video. Goodbye.